So hi, while I'm waiting for some components to arrive for my next big build, I decided to take a quick look at these little multifunction tester units that lots of people have on their bench and some people might be thinking of buying. Now, in a previous video I talked about capacitance meters, and I've got a fairly expensive capacitance meter, but it still failed to detect some problems. And recently I was doing some tests in other circuits, and I was looking at transistors and diodes, and I tested them using the normal method, which is to get the multimeter out and to test it in a forward direction, test it in a backwards direction, and my multimeter's got some pretty good facilities for that, but it failed to detect a problem. And I popped the parts out and I popped them into these devices, the little one at the front mainly, and it too failed to detect a problem. I was still suspicious, so I popped in a replacement part and the device worked perfectly after that. So these are very limited. They're limited in voltage and they're limited in testing current in particular. Now, this peak Atlas DCA75 does have a slightly higher current and slightly higher testing voltages. So I'm hoping that will overcome some of those problems, and hopefully it should also produce a lot more data about the device that's under test than the other ones do. But anyway, I'm going to put it out of the way for the moment and we will focus on the other devices. First up, we're going to look at this little device. And this is actually an EEPROM programmer, and I'll put the part number on the screen. It's a bit hard to read while I'm doing the video, but yeah, normally you program EEPROMs or EPROMs on it, but you can also just pop a logic device in, and with the latest firmware it has tests for a lot of 7.4 logic and similar logic devices. Pop it in, type in the number, press the test button, and it will tell you if the gates work. Now, it does not test complex stuff like timing parameters, edges, the speed of edges, and all that sort of stuff that you need for a full characterization of the logic device. But it does give you a quick indication whether the device is working or not. And that's pretty much what all of these testers are going to do in their respective domains. So moving on to more common components, I'm going to just focus, I think, on diodes and transistors. That's enough scope to cover with these. Many of them will do resistance and capacitors and things like that as well. I'm going to start off though with the little one in the front, and yeah, you get these on eBay for about £10–11. If you want a really posh one that'll do things like what's the word I'm looking for, remote control decoding and things like that, the little infrared pulses, then you might move up to £14–15 and £16 if you want a case. But yeah, first up we will take a little transistor that's been reclaimed off a board and do a swift little test with it. And I quite like this one because, you know, often you can just shove a component in and you press the test button, and provided that the battery is charged up, it doesn't really care too much what the leads are. And we can see that there's like 1, 2, 3 multiple ways of plugging in your component, and there's a completely useless surface mount section on the right. But here we go, we've got a N-channel JFET here, and it's measured VGS, which is the voltage at which it switches off conduction at 1.4 volts, which is a slightly surprising voltage, I've got to be honest, but this might well be faulty, so we'll see. And the current that it's using for that is 2 milliamps. So at 2 milliamps, I would say that isn't really turned off. But anyway, we will see. Let's plug in another device, and I think this one is a 3904, and that's the 2N3904. Okay, and it's showing an HFE of 120 and voltage forwards across the base emitter of 706 millivolts, and that's all it's actually showing us. So there's some information that it's detected it as a transistor, which means that it is actually operating as a transistor. If, for example, collector emitter was shorted, then we would see that, or it might show up as a weird diode configuration instead. So I'm going to take a real 2N3904, plug it in, and that's because I think that HFE was low. Yeah, there we go. I was expecting about 200, and the previous one was quite low. 682 millivolts forward voltage drops, which is about right. You'd expect about 0.7. Okay, let's move on to the Peak Atlas. So these are a bit more pricey. This is a DCA75. It takes a single 12-volt battery in there. I think the new ones, this is several years old, I think the new ones actually take a different type of battery and probably have some upgrades to firmware and things, but as we'll see, there's no problem with this one at all. And it is mainly focused at things like transistors. So I think I'm doing up the 2N3905 again. To be honest, they're all a bit mixed up on the bench. It's a bit hard. Here we go, analyzing, and it's an NPN silicon transistor. Great. Scroll. There's my identifies the pinouts, and I actually use that quite a lot if I've got a transistor to stick it in to find out what the pinouts are, and the HFE and the current. And the current it measured at was a bit higher than on the previous one, and VBE 0.79, which is a shade high, I think. But it measured current base at 4.5 milliamps. That's the measurement. So we've instantly got a lot more data than we had on the previous tester. Now this tester is about 40 or 50 pounds, and the one we looked at a second ago was 10 pounds. So yeah, you're paying for that information. Really, would I buy this one versus the other one? Oh, you know, I probably would just buy the cheap one for quick tests, because although this has more information, it's not that useful in isolation. It just gives you a slightly more complete picture of what you're doing. So the DCA75 is slightly different. It does all the same things that we saw before. It has a slightly higher voltage, which is quite helpful, and some slightly higher current, which is also fairly helpful. And I'm going to just join up the same transistor that we were using before. It should give us a fair bit more detail than we saw on the previous devices, and I'm using it just in standalone mode at the moment. It does have a USB plugged in at the top, but it's doing nothing really. We're just applying power. I like to join these up in the same order. Fingers and thumbs today, but RGB. So I hold the device one way around and join them up, and you could say that's a medical condition, but there is actually a reason for that, and that's when I test multiple devices. I want to be using the same leads on the same point on the device when I'm comparing. So here we go, HFE 122, red, green, blue, all set out neatly. So we're seeing 3 lines of data on the display instead of 2, and a pretty picture of a transistor, NPN. So that's all very nice, and we can start scrolling through the data that we have available. So here we go. So yeah, we've got the current at which it measured that HFE, the VBE 0.782, which is a little high, as I said before, the current base 5 milliamps now. And we've got VC saturation, which is incredibly important, and so we've got a measurement of that at 0.04, 40 millivolts, and the current that it was done at, and the base current that was measured at. So that's pretty handy stuff. Certainly if you want to match this against an equivalent, for example, in a data sheet, that's handy to have around. But it's not really doing that much more. We've got an extra reading, the saturation voltage reading. Okay, so the real trick with this is its ability to graph things on the computer. So yeah, for those interested, this is a picture that I took myself, and it's of Valencia. So let's kick off the software and take a quick look. Hopefully we can see everything clearly. So here's our software, and it's grabbed the existing reading of a device that I've already got plugged in, which is the NFET, so the N-channel JFET. Taking a quick look at the screen, on the left hand side we've got the same data that we had on the device. It's just all in one long list. Then we've got a nice picture with the color coded terminals, and then on the right hand side we've got a greater explanation of the measurements that it's done. So for example, it will tell you at what current it measured the HFE and voltages and all of that sort of stuff, and it expands it all out into kind of like English sentences. So that's quite nice actually. Switching to the first of the graphs, we've got a graph of ID, current drain versus VDS, voltage drain source, and in the bottom left hand side is a section where it's decided what voltages and currents to test at. So VGS and VDD, and VGS will be stepped, and we'll see that on the display in just a few moments. Now these settings down at the bottom left hand side can be altered. We can modify, for example, the sweep of the graphs, but within limits. It only runs to 12 volts and it only runs to about 10 milliamps, although we'll see it really goes to about 11 in practice. So there we have it, a fairly typical curve for a N-channel JFET. Now, one of the things that I can do here, of course, I think I mentioned it before, is I can change the parameters of the sweep somewhat. So I've got various voltages stepped here, and I can change those so I've got different voltages and a slightly different sweep, but within the limits of 12 milliamps and 12 volts. So I'm rerunning that sweep again with the new settings, and I'm going to test this against another part. So these are two JFETs that I've taken off some boards, and I believe one of them is faulty. So I'm just going to do a sort of head-to-head comparison, and this will keep both traces on the screen together. So the first one's nearly finished, and then what I'll do is I'll plug in the second one, identify it, and I'll plug it in with the same color coding on the leads, so that I'm not having any variability in the internal circuitry of the tester. It's all down to the device under test. So we'll get that plugged in and we'll rerun the trace. So first up, we're going to run the identity screen again. In fairness, if we know we've got the same parts all the time, then we don't really need to keep going back to this. We could just keep rerunning the test. But in this case, it's useful. It shows me that some of the voltages have quite significant differences. So over 4 volts, for example, instead of 2. So we'll see what happens when we look at the traces then. Okay, here we go. And it's very pale colour, unfortunately, but we can already see the first trace is miles higher than the original. There's the second one, and yeah, and the graph's having to rescale just to fit these in. So these are notionally the same device. So an HP part number, I can't actually find out an equivalent for it, but we can see that the two supposedly the same JFETs are behaving like completely different devices. Now, so there's our 2, and our 2 for the other one is way above it. So we're talking 500 microamps versus 5 milliamps. So big difference, times 10 on the current scale. Now, if we knew what the device was, we could look this up in a data sheet and we could understand which of the two is faulty. I don't have that luxury, so I have to look at the circuit diagram where they're being used. And I can come to the conclusion the second device is okay and the first one is not, and that's because of the way it's being used as a switch within the capacitor charging section of an integrator circuit. So I can reason that. To be certain, I'm ordering a new old stock from Switzerland, and I will test that, and that will then go into my library as kind of like a test template of this was a good known one of these N-channel JFETs. So let's take a look at a couple of other devices. I'm going to do a 2N3904, and this is a device that I might want to save the graph for as well. So here we've got the result on the screen, and yeah, I might want to save the result from this so that I can use it as a template to compare devices under test at a future date. If I've got a known good result, then that's really useful. Of course, I'm not the best organized person. It might take me a while to build up such a library. So it's now offered a different graph, and there are about 5 graphs at the top now for the BJT. and it has also suggested the test parameters as well. I'm running that at the moment, and yeah, we can see our current, our typical graph of collector current versus VCE. Now remember, as before, VCE is not the same as the voltage we are applying. It's the voltage across collector emitter, and there will be a resistor in series, which we can see in the diagram that's sort of popped up in the bottom right hand corner here. But yeah, there is a typical example of the curves for a 2N3904. So just like before, we can compare two devices. So this is the 2904 that I thought was a bit iffy. So we can see 55 microamps up here, 55 microamps down here for the second device. So the gain is very much lower, but we can't necessarily see a lot more than that on this particular graph. I can actually see there is some compression in the HFE depending upon that that base current, but we'll see more of that in a second. All we can see at the moment is the HFE is considerably lower. So I've decided to plot the HFE against VCE. Now, it is normal for HFE to vary according to VCE, and we've finished the plot now, and we can see actually that it varies quite a lot according to the base current as well, and that seems excessive to me, and particularly at the lower end that looks pretty bad. So yeah, it's absolutely normal for HFE to vary according to VCE, but you shouldn't expect to see that much variance. So I am going to plug in a known good device, and we shall rerun this, and I've locked the settings so that we're going to rerun it with exactly the same test conditions. And here we go. So we just identify the device again. And really we just do this just in case I've mixed up the cables. Okay, hit the button and let's see what happens. So unfortunately this trace is really faint, but here it's going up the left hand side, and in actual fact with the settings for the original transistor it is so high that it is not managing to it's actually saturating. But anyway, we'll be there in a second, we'll think with it. Here we go, here's our first trace. So that's our 60 microamp trace, and here's our next trace coming up, and look at that. So this is our 40 microamp trace, and it is running exactly along the same line as the 60 microamp. And so this is what we'd expect to see, a slight slope because of the effect of VCE on HFE, but we wouldn't expect to see the base current affecting it at all. So from that graph we now know that this candidate transistor that I've taken off a board is not behaving as it should do. So good news, we've found a faulty component. But the thing is, you know, all of our previous tests with the cheap testers were unable to identify that. We need to have some knowledge of transistors in order to use this more advanced tester. In fairness, I will say this tester is still somewhat limited, with only 12 milliamps and 12 volts to test with. We really can't go to the levels that we need to test all devices, and so for example Zener diodes we can only test to about 10 volts and things like that. There are just, you know, practical limits. I would really like to see them make this with a much higher current, say 100 milliamps and 30 volts. It'd be great then. And I've looked for a few other curve traces on the internet that could do that, and they're all very pricey, so or really poor quality. So I might end up making my own. We'll see what happens. So I've tested a normal silicon diode, and you can see here the typical 7 volt, 0.7 volt transition region, and that's absolutely fine. And here I'm testing a Zener in reverse, and it's showing a different type of curve. Unfortunately, I run out of current with that test. Now, what I'm going to do, and we see that the graph has changed to a PN junction IV graph, which is perfectly typical. Now, what I'm going to do is I'm going to use this hopefully to identify some germanium diodes and look at their characteristics, which could be quite variable, and also identify if some of them are fake, because one of the things that happens with germanium diodes when you buy them new nowadays is they're often Schottky diodes, not germanium. There's more to a germanium diode than just having a small forward voltage. So let's give that a go. So I've got on the graph already a 1N4148 typical silicon diode trace, just to use as a comparator, and I'm trying these 1N60p germaniums, and we'll just see what they do. So I'm expecting to see a much shallower curve starting a lot further back towards the 0 volts. And if it's a fake, if it's a Schottky diode, then we'll see a similar curve to the silicon, just starting to the left. So it's the more gentle sweep that we hope for. Here we go. Okay, and that is a typical silicon curve for a Schottky diode. Fake. So the reason this matters for me is because I actually want to use these in some RF detectors, and it's actually that curve at the bottom, which is exponential in nature or logarithmic in nature, that I want to use in the detector, because we're interested in power, not linear voltage. This is a fake. I can't use it for that purpose. So just running a second sample from the same bag, and yeah, exactly the same result. So I do have some other germanium diodes from different suppliers. These from a guy on eBay are supposed to be new old stock, and yeah, they look the part. They look old and what have you, but we'll give it a go. Just join it the right way around and see what happens. Yeah, unfortunately we've got the very pale blue, but it is pretty much tracking those original set almost identically, so I'm going to go for Schottky again. Sorry. Okay, and just to be sure, we'll test another one from the same bag, see what happens with that. And the same thing. So third attempt. So I mean, there's nothing wrong with these diodes as such, except they just are not what they claim to be. They're behaving as diodes, no doubt about that. Here we go, third attempt, same bag, and yeah, and the same depressing silicon trace. So just to prove that it isn't just my imagination, I thought I would look up a characteristic curve of a 1N34A diode, which is what I just tested in that last test, and the curve is here. Now this guy has only tested up to 0.5 volts, but there's a very significant difference in this curve. Our curve doesn't even reach 0.5 volts. If we look at that, so this curve is significantly gentler. So we can look at a particular point on the curve and we can try and correlate it to the data on my sheet, and we're not even there. So yeah, there we go. That's kind of where we should be. So anyway, let's go and look at some more diodes then in that case. So this is my last pack. It looks a fair bit different again. None of them have looked the same really. Here we go. Oh yeah, look at that. One germanium diode curve. Finally. So as before, I'll run a second one from the same batch. And yeah, okay, there we go. And actually, yeah, we're seeing the variability that I talked about there, that I expected to see in the germaniums. Cool. But certainly we have a much more gentle slope, starting at a nice low voltage. Typical germanium action. So I have found another bag, and we can see the rather interesting traces that have come from that on the right hand side, which are very germanium in nature, but really slow. And I would say that I'd have to treat those as faulty. Let me just delete those traces, and the third one has just run up. And yeah, I'm kind of a lot happier with that final trace, but that's 3 diodes out of one batch, and 2 really were faulty, and this one looks okay. In fact, it's a really nice germanium curve that I can use in my RF detector circuit. So there we have it. At the low end of the scale, the cheap eBay tester was perfectly adequate. It did the basic tests, and it wasn't until we got up to the DCA75 here, which I bought from CPC Final, because that was by far the cheapest place I found it. Anyway, this was able to differentiate a lot more and identify more faulty components, but it's still quite limited because of its voltage and current range. Still, I'm not going to do any more tests. There's dozens more things that we could look at, but hopefully you enjoyed that. If you liked it, please give it a thumbs up, click the like button, subscribe of course if you haven't already done so, and please leave some comments down below. I'll see you next time. Take care.